This is Chapter 9, Geologic Time, Lecture 2, and we'll pick up here with how are fossils preserved. All right, so if you have something like shells or hard parts like bones, those are the easiest things to preserve in the fossil record. So we have shells here, we have bones that are fossilized, we have replacement of structures like trees into petrified wood. You could also just have an impression or a cast or mold into sediment preserved. And with replacement, that's where you get fossil preservation when silica or pyrite, something similar to that, replaces the original structure. Or you could have a thin carbon film that occurs because of burial, with carbon-rich plants then becoming thin films of carbon. This is a fern, for example. You could also have impressions. I think this is from the Green River Formation in Wyoming, but I could be wrong. Fish and other soft creatures can be preserved as impressions, especially in quiet water, slow-moving water. Amber can also trap insects. That would be tree sap, really, that trapped an insect and is preserved for quite some time, like in Jurassic Park. Or a constructed feature. You have this where some fossils don't preserve the actual organism, but they preserve something the organism constructed, like this stromatolite. And we recognize these in the field because we see these sort of sinuous structures, and they stick out. All right. So, traces of creatures can be found in the rock record. These are footprints. We call that a trace fossil. It's not the creature itself, it's something the creature left behind. From that, we can infer gait or weight of the animal, whether it hung out in a pack or if it was all alone. Burrows of worms are also trace fossils. It's not the worm, it's the burrow that the worm left behind. A worm is very soft. It doesn't have any hard parts that can be replaced by mineralization so easily. I mean, maybe a little of the worm, but most of the worm, no, cannot be replaced so easily. So we don't see that in the fossil record. How would we try to figure out what kind of creature made this? We'd kind of look at the size of the burrow too, the length, the depositional environment. That could point us to who is responsible for all these burrows. All right, so throughout geologic time, we see different types of fossils. Okay, so in the Precambrian, the fossil record has these simple creatures, such as stromatolites. Okay, and they left these structures. Now going into Paleozoic, we see things like crinoids, coral, clams, certain fish, plants, insects, and amphibians preserved in the fossil record. They were buried, remineralized to what you see today as fossils. And after that, showing up in the fossil record in the Mesozoic, you see dinosaurs and flowering plants. And then in the Cenozoic, we have mammals and grasses preserved in the fossil record. And that's a mammoth. We can also look at how fossils change in a sequence of sedimentary rocks. This can look a little overwhelming at first, but we'll break it down. What we see is that the fossils change up the section of rock in a systematic way. And what these letters are showing you is the span of where we see a specific fossil. So like this trilobite with A only occurs here in the lower units. B, we see it all the way up here. C, here. The longest span of a fossil, this looks like a gastropod, would be E. So we see it all throughout these rocks in the section. And the shortest appearance would be this brachiopod at F. We call that faunal succession. So yeah, some of these species lived a short time span, so we only have a narrow age range, and some had long span of time where they existed. You can overlap two different types of fossils to constrain the age of the rocks. We can do that with G and H. If we see both H and G, we know it's from a very specific point in time because we don't see that overlap in any of the other rocks. So these two sections of rock contain many of the same fossils. We can match the two sections. We can draw dashed lines connecting the places where the two sections correlate or represent the same time in geologic history. And we have letters between like the same fossils, so I, G, F, C is only in one of these. So some units C and H are present in the left section but not in the right one. We'd say they sort of pinch out. And I can draw that here wherever you see like a pointed thing. We know that we don't find that fossil in the section on the right. So their position is marked by a disconformity or a simple bedding plane. This would be a disconformity. It looks like an erosion surface. This would just be a simple bedding plane. Either the layer was deposited but removed by erosion, or was never deposited in the right section. Okay. And we don't necessarily need fossils for this, do we? We can just look at rock types and see how they correlate in different sections. So a geologist would look at a section of rocks, measure the thickness of each section, and summarize it in a stratigraphic column. And you take two of them from known areas, and you can draw imaginary lines between them and infer how these rocks are continuous throughout the subsurface, or were continuous throughout the surface of a rock unit. So we don't need to know everything about every part of a unit of rocks if we have enough stratigraphic columns to help us infer changes in the rocks there. Okay, so we'll look at how they correlate. So we have units 1 through 9 really. Using both these sections, we can reconstruct a more complete section. So units 1, 2, and 3 are present only in the left section, and units 7, 8, and 9 are present only in the right section. The changes in thickness of these sediments, like 5 gets thicker to the right, that may be due to changes in depositional environment with the availability of sediment, or differences in the rate of deposition. That's kind of generic, but you're not going to see a landscape where every part of a specific rock unit is the same thickness forever. You know, there's variability in how sediments were deposited. So the units that can be correlated are 4, 5, and 6 because we see them in both sections. All right, now to the geologic time scale. This time scale is used to correlate rock units across countries and continents and to have a standard vocabulary for describing time. You'll find that a lot of these names are from the UK because they were first named there. Okay. The boundary between the Precambrian and the Cambrian Paleozoic, it's based on a widespread appearance of hard-shelled organisms. We're looking at eras and periods of geologic time here. You start off with the era and then you subdivide based on different appearances of rock types and fossils and extinction of different creatures. This boundary between the Paleozoic and the Mesozoic is based on a major mass extinction called the Great Dying. And we say they're extinct because they're no longer in the fossil record. They just did not appear to be living at that time. And then between the Mesozoic and the Cenozoic, it's also a mass extinction. We saw the disappearance of a lot of dinosaurs, but not all of them. We still have cool things like alligators and birds and crocodiles that persist. But the huge ones, we don't see them anymore. So yeah, these era boundaries are based on appearance or disappearance of certain types of life. Okay. So we want to assign numeric ages to our geologic time scale. And what is that based on? We could, say, use radioactive dating to determine a numeric age for this volcanic layer on the left to help constrain the ages of the sedimentary layers on either side of the volcanic layer. So these are sedimentary and this is volcanic. And just for reference, I would know that because often volcanic layers are displayed with these types of icons. And these brick appearance is almost always limestone. It should be, otherwise that's confusing for a geologist. And these dashed lines kind of implies shale or mud rock to me. These dots implies sandstone. Just for reference, you don't have to memorize that, but that's kind of our visual language. You could also date clasts or pebbles that broke off from a volcanic, or igneous, I should say, dike. And remember that a fossil-bearing layer that is cross-cut by a dike must be older than that dike. If you obtain numeric ages for the dike, cutting the fossil-bearing bed, you can constrain its age. Okay. So furthermore, using the time scale to assign numeric ages. Fossils can be assigned to a time period, and then the age for that period provides an estimate for the age of the fossil-bearing layer. So here we have a fossil-bearing tilted bed. There's an unconformity here. And then we have a fossil-bearing layer above that unconformity and looks like some kind of sand unit on top. So the unconformity can be bracketed using fossils and the time scale to assign ages to the rocks above and below the unconformity. So the underlying rocks, for example, could have Jurassic dinosaur fossils, say from 160 million years ago, but the overlying layer has early Cenozoic mammal fossils from 60 million years ago. So we know then that the unconformity is between 160 and 60 MA, and that's what I mean by bracketing that age. The example on the right, we also have an unconformity. We could bracket that age of the unconformity by assigning a numeric age to the granite through radioactive decay age dating, along with an age assigned to the fossils. We have a fossil bed here over top. Say the granite is numerically dated at 80 MA, whereas the overlying fossil beds are early Cenozoic, 60 MA. So we'd know that the unconformity formed sometime between 80 and 60 MA. All right. There's a few things that tell us that Earth history is long. One thing that we can all observe is that tree rings record annual growth cycles. So the thickness patterns in, say, these pine tree rings can be correlated from living trees to dead ones. All right, so that's some kind of uniformitarianism. You can look at seasonal layers and ice cores. What ice we still have on this planet is an excellent record of past Earth history. We also have seasonal layers in varved sediment from lakes. If you take a core of lake sediment, it looks something like this. Maybe not always as contrasted varves, but yeah, you'll get seasonal layers in any kind of lake sediment. Those are alternating light and dark sediments. The Green River Formation in Wyoming and Utah includes millions of varves. So that formation spans at least several million years. And we can observe varves from the last several years in modern lakes. So we compare what we have there to things in the rock record, and that's really cool. We also can look at current rates of plate motion. And that currently indicates that the Atlantic Ocean took 100 million years to form as Africa and North America, South America moved apart. So we look at processes today and we look at processes in the past to understand Earth history a little better. So where does the age of the Earth come from? We can look at meteorites. Meteorites, analyses of them support the formation of the solar system and Earth between about 4.53 and 4.58 billion years ago. And that would have hit, and had an impact on the planet. And let me put it this way, the little internal clock of minerals within that would have been reset. We can date it. Okay, 4.55 billion. We can date moon rocks as well at 4.5 billion years. This is all very generic overview information. If you want to look deeper into it, I definitely encourage you to do so. The oldest Earth rocks that we can date from zircons within them, that's a mineral within, that'd be 3.9 to say 4 billion years. Individual grains within that being 4.3 billion years old. So remember, a rock can contain older pieces of rock. Broadly speaking, we can look at data on the age of the solar system and the universe. So thinking about that, we can observe what happens when an asteroid, comet, or other meteoroid hits the surface of a planet or moon. So during impact, the object breaks apart and sends shock waves in all directions throughout the subsurface. And then ejected material from the object and the underlying material spreads out in all directions. If the impact is not too large, a simple crater forms. If it's larger, generally speaking, it can form complex cratering as the shock waves converge. So this is more complex than just one simple crater. And with that, you get rocks that might look like this. This is an impact breccia with fragments in a matrix that was actually melt produced by an impact. So older pieces of rock contained in a younger matrix. We can also look at how the oxygen content of the Earth's atmosphere has changed over time in this chart. So we have time as billions of years ago on the x-axis and percent of O2 in the atmosphere on the y-axis. In the Archean, we had little to no oxygen in the atmosphere. This can be inferred from rocks. Over time, in the Proterozoic, we have the first appearance of free O2 in the atmosphere. We call that the Great Oxygenation Event. But something really took off after that. Well, yeah, that would be the second oxygenation event. Say about halfway through Earth's history, enough oxygen was added to the atmosphere to allow iron in the oceans to oxidize, forming iron formations. And we kind of see that to present at this level. So what you have corresponding with this in the Archean, you do have volcanoes emitting gases including CO2 and SO2. And then algae helped increase oxygen through photosynthesis, these sort of simple living things. And further increase in oxygen caused iron to be deposited in oceans. And this is a banded iron formation. We have these in Marquette, Michigan, and in Minnesota, and they're really cool. They tell us that the Earth was really changing around this time to deposit such a thing. Oh, you also find them in Ontario, so we're not far from these things. Okay. So back to Precambrian life. I talk about stromatolites. Those are our earliest non-microscopic fossils identified on Earth, but they were created by microscopic creatures. And I'd say they're pretty easily identifiable if you're walking up to an outcrop in, say, Montana. I've seen quite a few in place there in limestone. And then bacteria, about 2 billion years ago, bacteria had produced enough oxygen through photosynthesis to increase the amount of oxygen in the atmosphere, and then that provided a protective ozone layer. Okay, so you had these volcanic emissions, and then you had these microorganisms adding to oxygen. After which we see in the geologic record a Cambrian explosion, and we see things called trilobites. They had these external skeletons, and they were very diverse in appearance. They're all different types of trilobites, which is pretty cool. And then brachiopods. I love brachiopods. The Cambrian seas had a lot of different types of brachiopods as well, thriving with the oxygenated planet. So, thinking about the Paleozoic, I love these illustrations. What would that have looked like? Well, in the early Paleozoic, we'd have corals, crinoids, mollusks, trilobites, snails, shelled creatures with tentacles like squid. In the middle Paleozoic, we start to see a diversity of fish, and then insects, and then plants, including ferns and seedless trees. And then in the late Paleozoic, we had amphibians and early reptiles evolving. Now in the Mesozoic, the early Mesozoic, or the Triassic, we got these small dinosaur-like creatures, early mammals, and seed-bearing conifers. In the middle Mesozoic, with the Jurassic, we see a diversity of dinosaurs. Seas had a lot of things like ammonites, which is a sort of squid creature with a beautiful shell, spiral shell, starfish, and then large marine reptiles. In the late Mesozoic Cretaceous, we saw flying reptiles, flowering plants, those are called angiosperms, turtles, and plankton. And getting to what is more familiar, the Cenozoic. In the early Cenozoic, we see the appearance of bats, rodents, primates, sloths, whales, hoofed animals, marsupials, and small horses. And in the late Cenozoic, we see appearing the first humans and familiar creatures like the woolly mammoth, well, and beyond that. These sorts of birds. I don't know if looks like an armadillo, bison, everyone existing in harmony here, I hope. All right. So, back to correlating stratigraphic columns and events. We can look at these two sections and look at how each layer correlates or doesn't from one section to another. We can, of course, use rock types, position within the sedimentary sequence, fossils, numeric ages from radioactive decay, or a magnetic sequence, which isn't something we've talked about much since looking at seafloor data and plate tectonics. So with rock types, a unit may have distinctive characteristics that enable it to be matched across two sections. With the position and sequence, you have two different types that might correlate if they are in the same position in the sections. With fossils, if the same fossil exists in both sections, the ages are correlative. And with the numeric ages, if you've got datable units that show the same age, they probably correlate. With a magnetic sequence, two units might record the same sequence of reversals of the Earth's magnetic field. All right, so we've got these faint correlation lines, of course, for reference. Now to this block diagram. We can consider how rock units could change from one section of rocks to another. So you have an ocean to land deposits. There's a river discharging into the ocean, and there's a delta that's formed as the energy level goes down. What you have is a lateral change in sedimentary environment. And with that, we'd say we have a facies change. The environment and type of sediment deposited at the same time can change from one place to another, because here we have an ocean and here we're on land. So different facies will exist. You can also have a restricted event. A unit might not be present in nearby sequences because it simply wasn't deposited there. And that sounds simple, but I myself had trouble with that as a student to say, you know, why do we see a sandy unit here, but not over here? This is a reconstructed environment. Sometimes all we have are rock outcrops to look at. We can also see changes in thicknesses. That can reflect variations in topography, because this sort of folded syncline looking structure accommodates thicker sediment in the middle. Or it can be due to a change in facies. You also can have at the same time layers being eroded away. So a unit might not be present because it was partly or completely eroded away. Now we're putting things together. I mentioned earlier with this chapter, probably in the first lecture, that a lot of times we're only looking at two events in one image. Well, there's a lot in this image, so we'll try to determine the sequence of events carefully. All right. Now I can do it one by one, but I don't want to. I'm just going to put it all out for you there. And you can flip back to where things aren't numbered if you want to try to compare. So let's see. First of all, we have our first unit here. It's probably igneous in nature. That's our bedrock. Okay. Second event is this sort of intrusion, like a batholith comes in. Okay. Third event that we see is some kind of erosion and unconformity, because we see it here and we see it here as well. Fourth event is just another unit deposited. These are separated by a fault, but it didn't happen yet. The fifth unit and the sixth unit, more deposition. Same with the seventh. After which we have a disconformity as 8. And then 9, we only see that right about here. The 10th event is a lava flow / volcanic eruption / dike. So this all happened. All right. And after that, a fault was formed. Some sort of tectonic activity here caused all these rocks to be displaced. And it also formed a fault scarp on the land surface. Okay. After which, a river ran through it, formed a canyon, deposited river gravel as the last event that we see. Okay. So sometimes you just have to take the puzzle apart, think about each piece, and try to put it together in sequence. It wouldn't normally happen this fast, but we have the answer sitting in front of us. Okay. We'll look at these figures and think about how the information is important in determining potential for geologic hazards. All right, so starting at the top, we've got these lava flows. You can use isotopic methods to assign ages to the rocks or observe the amount of erosion. And that tells us about how recently a volcano erupted. You might remember from the volcano lecture I talked about the ages of the Yellowstone caldera eruption and how, based on those dates, it could happen relatively soon again. Maybe, probably not in our lifetime, but yeah, we use those ages to kind of look at what might happen in the future too. All right, we can look at the age of fault scarps. That's what you see at the surface when there's displacement due to fault movement. You can see it's downdropped right here. Earthquake-related scarps can be investigated by examining soils and by dating sediments associated with faulting. So right after an earthquake happens, this scarp can form, which is kind of exciting for a geologist to go look at this brand new feature that showed up. And we can look at ages of terraces to determine ages of terraces from soil development. We can use, say, carbon-14 on charcoal in soil or sediment, or we could use other surface dating methods to determine the ages of terraces. All right, we've got this satellite image / block diagram of the Grand Canyon. All right, so the Colorado River flows from right to left, and it enters Lake Mead. The Grand Canyon is eroded into the Colorado Plateau, which is mostly flat-lying Mesozoic and Paleozoic sedimentary rocks. And the deepest part of the canyon It's where we have a cut through the uplifted Kaibab Plateau. Right about here. Okay, so we got the canyon itself. We got the Colorado Plateau. We've got a cross section. A to, can't read this. E, is it? Or B? I don't know. Okay, but here's the cross section. The oldest rocks are metamorphic and granites located at the bottom of the cross section. They are overlain by tilted late Precambrian sedimentary and volcanic rocks, and that's an angular unconformity. Okay. Right about here. And then we have Mesozoic sedimentary rocks, which contain dinosaur tracks and petrified wood in the Painted Desert. We also have like basalts and basalt flows that predate the main canyon. It was dated by Archon methods, I believe, to be 8 million years ago. Some basalt flows flowed into the canyon, demonstrating that some of the canyon is older than 4 to 5 million years. And then we have these faults cross-cutting the region, down-dropping rocks to the west and cutting basalt flows that are less than 1 to 2 million years old. So what I want to take from that is there is a whole lot going on here. Simply put. So we've got a couple parts to the geologic history of the Grand Canyon. Kind of summarizing what I said before, I like to start at the bottom with the first event. You've got your basement rocks, and then there was uplift and erosion of the basement, followed by deposition of late Precambrian rocks and a lower unconformity, and then tilting and an upper unconformity. Okay. Leading into part 2. On top of that, you'd have deposition of early and middle Paleozoic units, because seas now covered the land and deposited sandstone, shale, and limestone. Has some nice fossils in that. After that, we had a diversity of sedimentary environments, and those rocks were deposited in shallow marine environments, shorelines, and rivers. Then we saw deformation, uplift, and erosion. Although the Paleozoic rocks, they're nearly flat except a few faults and folds. All right, there's more to it than that. That's only through the Paleozoic. But we can look at this stratigraphic section and kind of match the main units and unconformities between the section that someone drew and the photographs that someone took as well. Okay, so this is what the Precambrian basin looks like, or basement, excuse me, looks like. Then you've got these late Precambrian rocks. You can see they're not quite flat. And a lower unconformity between the two. Then we have our early Paleozoic rocks from shallow seas. There's an upper unconformity between the late Precambrian, early Paleozoic. Then you have middle Paleozoic. Like I said, a diversity of sedimentary environments there. And the late Paleozoic rocks on top. Okay, and we will actually stop there. There's always the option to look at these investigations in your book, but we're not going to go over it in this lecture.